talked about last lecture. So let's see, so we're talking generally about multipartite systems, but we're restricting our attention to the case of bipartite. And so one concept we introduced was the notion of the marginal state, which is often also called the reduced density operator, but I tend to like the term marginal state better because it really is the quantum equivalent of marginalization of a joint probability distribution down to the distribution on one of the random, or some fewer number of the random variables. And the way that one does that is if you have some arbitrary joint state of the bipartite system, then the states of the subsystems are given by tracing over the other subsystem, okay? So that's what's sometimes known as the partial trace.
And that's the sum is over to dB on one top?
Correct, thank you. Yes. Indeed. So that's the, so this is the trace, but it's really the partial trace because I'm only tracing over one part. Right. And what we learned last time, if we hadn't seen it before, was that if the joint state of the system is pure, then the states of the subsystems are generally mixed. And that's true when the state is entangled, if and only if the joint state of the system is entangled. And that, as we discussed last time, is really quite a profound difference between classical physics and quantum physics. And in order to quantify the amount of entanglement, the way we approach that is by thinking about a particular decomposition of the joint state of the system when it's pure in terms of the Schmidt decomposition. So there always exists a decomposition of the state in terms of a special basis such that it's a sum over just one index, even though we have two parts, as a superposition of orthonormal vectors. Those vectors we call the Schmidt vectors. And these, the superpositions thereof is known as, are the Schmidt coefficients. And the total number of such coefficients is known as the Schmidt rank. Okay? So the state is entangled if the Schmidt rank is greater than 1. And a coarse way of saying how much entanglement is to ask, what is the Schmidt rank? But a more precise way of quantifying the amount of entanglement in the system is to look at the entropy of the probability distribution in the Schmidt basis. And in particular, if we marginalize and look at the marginal states, or the reduced density operators for the two subsystems, then this Schmidt decomposition takes on additional meaning. That is to say, the squares of the Schmidt coefficients are the eigenvalues of the reduced density operators. So they tell us the amount of statistical mixture we have in the subsystems of the eigenvectors of the density matrix, which are the Schmidt vectors. Okay? And what we see is that they have the same spectral decomposition. So there's the same amount of mixture in these two systems when the overall state is pure. And so we can quantify the amount of entanglement that we have in the system by looking at basically the von Neumann entropy, defined as such, for the two states. which are in fact equal. That is, the entropy is equal. And that entropy varies from, can be at minimum 0, and that's if we had no entanglement. This is for a product of the two subsystems. Well, then each subsystem is in a pure state. And so each subsystem has no entropy because it's pure. To the case where we have the maximum entropy, which is what we would call a maximally entangled state. And this D here, although I didn't say it, is the dimension of the smaller of the two dimensions. So the most entanglement you could have depends on the smaller of the two dimensions that we have. So one problem we'll look at in homework that we've looked at last semester is the Jaynes-Cummings model. Remember, the Jaynes-Cummings model is the coupling of a two-level system to a mode of the field, to a simple harmonic oscillator. So what's the most entanglement that you can get between that single mode, which is an infinite dimensional system, and the qubit?
2.
Right, you can get, at dimension 2, you can get 1 bit of entanglement. So we'll revisit that problem. That is an example of a bipartite system in cavity QED, and to the degree to which we ignore leakage out the cavity and spontaneous emission, it's unitary evolution. It's of the sort that we were discussing, where you can get oscillatory behavior between generating entanglement and entanglement being, and then disentanglement, unitary disentanglement. And that'll help us understand those collapse and revivals that we saw last semester when we were looking at that problem. So it's good to review that one for homework again. All right, any questions about any of that? Yeah.
So in practice, if you wanted to get the Schmidt vectors for a bipartite state, could you just take its partial traces, or no, take its partial traces and diagonalize it matrices?
Close, but no cigar.
Oh.
And the reason is that you don't know the phase. And that's important. So if you look at, say, let's just look at two states. Right, these two states obviously have the same marginals, but they're different. They're orthogonal states. They're maximally different from one another. And that's sort of the point. You can't know the whole from the parts when the system is entangled. And you can't get that phase by looking at the individual subsystems. So there's no way to measure the whole system by just measuring the parts. You need to measure something jointly, is what we might call a Bell state measurement, right? You can't do that locally. So, I mean, in practice, I mean, you, as I say, you know, one rarely actually goes through this singular value decomposition and extracts. There might be some cases. Typically, what we're interested in is, you know, how entangled is the state? And for that, we don't need, we could just look at the marginals. That we can find out. But we can't know, we can say it's in that class of entangled states, but we can't say which one it is unless we measured the whole thing somehow.
Those states, it looks like they have the same Schmidt basis.
They don't, and that's a little bit tricky. So, because that's an important point. The Schmidt coefficients are positive numbers. Always, because they are the singular values of this matrix are always positive. The singular values, the lambda, are the eigen values of the square root of that matrix. And
So
so
those differ by just a minus sign or something? Or
they do,
basically.
exactly. So the Schmidt basis for this is, you know, the U's are these, and the V's are those. You know, they come in pairs. That's with the plus sign. With the minus sign, I believe these are the vectors. I believe that. I haven't done that decomposition in a while. And that I you would never find until you actually did the singular value decomposition. Good questions. Good to clarify those things. All right. Now, there is another point that I want to just finish off this discussion with, which is the question about entanglement and the choice of subsystem decomposition. So, in classical physics, we know that if I have some system with multiple degrees of freedom, I can often solve the system more easily if I choose the coordinate system correctly, right? In fact, the formal theory of Hamilton-Jacobi theory is all about choosing the right coordinate system such that you can automatically see that it's integrable. But a more generic, or something maybe more familiar is, you know, for example, in classical physics, we have examples of, so use the right coordinate system. To solve the problem easily. So for example, if we have coupled oscillators, we can solve the problem instantly using normal modes. So instead of using the coordinates of each oscillator, one uses the collective variables, normal modes, and then the system separates into normal mode coordinates, and then you have separated Hamiltonians, and the system is integrable. Another example, of course, that we know very well is the two-body problem. e.g., hydrogen, even just thought about as a classical bound state, right? So if I look at this, let me write down the Hamiltonian for this. I have the kinetic energy of the electron. I have the kinetic energy of the nucleus, the proton. And then I have the Coulomb energy. They're not A and B, they're electron and nucleus. Right? Now that problem is not separable in electron and nuclear coordinates. We see that there obviously is an interaction between the electron and nucleus. So this is not separable. But we know how to separate it. And we instead go to center of mass and relative coordinates. So we do change of coordinates to center of mass and relative. Right? And when we do that, then my Hamiltonian is, call it C, with a relative momentum, reduced mass, and then E squared over R. Right? And this is the Hamiltonian of the relative motion of the electron relative to the nucleus, or whatever it could be. It could be positronium, whatever you like. And this is the center of mass. Well, this isn't an operator. I mean, it could be an operator. I'm mixing my hats up here, but it doesn't really matter. It's the same deal. But the point here is now this is separable. But it's separable in a particular choice of coordinates. It's not separable in terms of these subsystems, electron and proton. But it is separable in terms of the center of mass and relative coordinates. And so if I now put the hats back on, everything, and this is, of course, tensor plot implicit. If you don't put it there, it doesn't matter, but it's there. Then the eigenstates of the system of a separable Hamiltonian are product states, right? So the eigenstates are the following. We have a free particle for the center of mass, and their usual hydrogenic states for the motion of the electron relative to the proton. And we usually don't worry about this because we don't reach the motion of the whole atom is typically treated classically. Of course, if you're doing laser cooling and getting to cold atoms, it's all about this. It's all about manipulating the quantum nature of the center of mass of the whole thing. So, you know, we care about these things sometimes. But the point really that I want to emphasize here is that this state, whether a state is entangled or not, depends on the subsystem decomposition you make. Okay, so this is separable in the center of mass and relative, but it's entangled in the electron and nucleus coordinates. The electron and nucleus or proton are entangled with one another. Or if it was positronium, if you had a positronium and the positronium decayed, the positron and the electron are entangled with one another. Even though the center of mass and the relative coordinate are not quantum correlated. So that's one important point I want to emphasize that we'll come back to because it caused a tremendous amount of confusion in quantum optics and it caused a big controversy for a while of whether or not a particular state we should consider to be an entangled state or not. And that really depends on what your subsystem decomposition is. Okay? And that hopefully has to do with what you're going to measure about the system. Right. So this comes to another point that I'll conclude with here about the notion of change of basis. So there's two kinds of notions that we often think about when we think about change of basis in this setting. There is a change of basis of the Hilbert space for each subsystem. Again, let me just restrict my attention to the bipartite case. So I have some Hilbert space associated with subsystem A, and I have some Hilbert space associated with subsystem B, and we have the tensor product space for the joint system. Now, of course, we can change basis on our Hilbert space. And one way we can change the basis is just to say, we started with some description of some standard basis, some canonical basis for subsystem A and for subsystem B. But in principle, I can change basis. And one way I could do that is just let's look at a different orthonormal basis for D. For subsystem A, and one for subsystem B. I could do that. And there is a unitary transformation that achieves that change of basis, right? And so if I wanted to change the basis, I could, for example, take my state and expand it in the original basis. We called that expansion gamma. But I could do this in a different basis, call that delta. Obviously, this is the same state, just expanded in a different basis. And there is a unitary transformation that takes me from this set of coefficients to that set of coefficients. Yeah. Yeah, okay, sorry. So, what is true, and perhaps obvious, maybe not, is that these two states have exactly the same entanglement. Okay, that's to say the Schmidt decomposition of this matrix is the same as that one. Okay? Because I haven't changed the entanglement. Why haven't I changed the entanglement? Well, you can see that because all I did to get from this to this is to apply a unitary transformation that took product states to product states. So, this coefficient is that inner product, which is right? And this operation is a separable unitary. It acts locally, whatever local means. It doesn't mean it's space or time. It just means on that system alone it doesn't affect. So this state has the same entanglement as that state. So changing the basis is often said, well, when you change the basis, you don't change the entanglement. However, you have to be careful. That's if what you're doing is changing the basis locally. Obviously, if you change the basis globally, you can change the entanglement of the system. And that's equivalent to changing the basis globally is equivalent to changing the subsystem decomposition of the state. So for example, let's consider two particles on a line. Okay, so now I'm talking about infinite dimensional grid spaces, but the same idea holds. Okay, so I have two particles that they have position xa and xb, right? And I can write my joint state of the system in terms of a wave function in those coordinates, okay? And I can ask whether or not this is an entangled state between these two guys. Yeah?
Got XA and XA.
I got an XA and XA, but I should have said XB. Yeah. So whether or not this is entangled or not, again, now I should say, this guy, we could also do a Schmidt decomposition for this, whereas this goes up to, well, it goes to the Schmidt rank, whatever it is, but that could be as big as infinity in this case, like a harmonic oscillator-like system with Schmidt wave functions. Continuous infinite dimensional systems also have Schmidt decompositions. Of course, they're not done in the same kind of matrix way, but some kind of integral kernel theory. However, I can change coordinates. I can go, for example, from this set of coordinates to, center of mass and relative coordinates, maybe with some normalization that looks like this. So that's a perfectly good basis change on my two-particle wave function. And if, for example, this state were a bound state of the two particles, then it might look entangled with respect to A and B, but separable with respect to these coordinates. So it's not exactly correct to say that a change of basis can't change the entanglement. You hear that said all the time, but it's just not true. It depends whether your basis change is a global basis change on the joint system or whether it's a local basis change on the two subsystems. If it's a local basis change, then absolutely you're not going to change the entanglement. But if it's a global one, it can. And we're going to see that next time in the context of the optical fields.
Looks like you will always have trouble then with the Pauli principle.
Do what?
The Pauli principle will always.
Okay, that's a very good question. So the issue of identical particles is very complicated in what we mean by entanglement. And because, of course, you always have to symmetrize the wave function, right? And so it looks like it's, in some sense, always entangled. And in a formal sense, the answer to that is yes. But whether that's useful entanglement or not is a more subtle question. And one way to quantify this question about identical particles is to say the following, to use second quantized notation. So if I have some orbitals that are, say, specified by creation and annihilation operators labeled by, say, I'll call this. Okay, so this is a two-particle state acting on the vacuum. Now, of course, if I were to write this in coordinate form, the wave function sort of might look like this. It's, you know, orbital 1, particle 1, orbital 2, well, let's call these A and B. So I'm confused, which is the particle and what's the orbital number. So there's two different orbitals and there's two different particles. And let's just say that the spin is, let's call these fermions, what the heck. So this state sure looks entangled. But in terms of this, it's a product. It's only a product of one term of this sort. So we would call this in terms of whether or not I had two separate orbitals. For all intents and purposes, if these two orbitals never overlap in space, this is unentangled. And we would say, you know, if I had some general set of orbitals, well, let's just say I have two particles. So this is a general two-particle state. Then I look at this matrix and I do a Schmidt decomposition of this, and that tells me the effective amount of entanglement that's useful in the system. But it is quite subtle indeed. Okay, that's all I wanted to say today. What we're going to do tomorrow, at the usual time, is look at entangled states in quantum optics and where they come from, how we make them, and then after the March meeting, at least when I get back from March meeting, we'll talk about how one uses those entangled states in studies of the EPR paradox and Bell's inequalities. So that's where we're headed. All right? Very good.